Right, so I'm just going to talk. So I'm Tobias. I'm a software design engineer with imagination. I'm also the current OpenGLES chair now. I've just taken over from Tom recently. I'm not going to talk to you about that today because we're here to talk about Vulkan. And I personally have been working on Vulkan pretty much since we first started talking about designing it. So it's basically the whole run that Tom talked about. So synchronization. I titled this called Keeping Your GPU Fed Without Getting It. One that point is better. So if you've got an application and you want to render something to the screen, then you've likely got a bunch of draw calls. You've likely got a bunch of draw calls that you want to get pushed to the GPU that you can render. And your GPU is there for a purpose, and that purpose is to render those things. So you kind of want to give it to them, and you want it to have it at all times. Oh, and you ruined the slide again. Ah, what is going on with this? Never mind, it's fine. The GPU is still there. And ideally you want to keep it as fed as often as possible. You don't want the GPU to be sat waiting around whilst you're sort of still defining what your commands are. You want your commands to be defined as soon as you know what they are, and you want your GPU to take that and work immediately. But you've got to be careful. If you do it wrong, you mess up, it will commit you. Right, so specifically what I mean by keeping it fed. Like I said, you don't want it to wait around for you to define operations. If you've got some CPU work to do, you ideally want your GPU to do something while that's happening. Even within the actual operations you want your GPU doing, there's a good chance that bits of those operations may take a lot of time or cause stalls on their own, such as memory accesses. And ideally, you want a lot of operations in flight at the same time so that it can hide the latency of those stalls. Draw calls themselves are actually pretty good at this. They've got a whole bunch of different pipeline stages we've talked about. They tend to have a lot of things in flight. GPUs are very parallel, so they've got a lot of different fragment shaders running at the same time and other shaders as well. So there's a good way, even within a set of draw calls, to provide these varied tasks. The basic principle is that you don't want to serialize your tasks. If you take a very naive approach, which I'm hoping none of you are doing, of basically defining your work on a CPU, firing it off onto the GPU, then waiting for that to complete, and then only then doing the next set of commands, and you're going to serialize the system, and the whole time you're defining stuff on the CPU, the GPU is doing it. Still happening. Right, out you come. Fine. That work? Yeah, right, arrows work, we'll use that. Fine. What you can do instead is you can pipeline it so that you can start your work on the GPU, and whilst that's happening, you can start finding your next CPU task ready for the next frame. And by doing that, you overlap. You get a lot more work done in the same amount of time without anything just sitting around waiting for no real reason. And equally, when it comes to even a set of draw calls, if the GPU was to serialize the vertex and fragment work, you'd get maybe 2 done in this time, but really, by pipelining, which is what all modern GPUs do, you can have your vertex and fragment work operating at the same time, basically, again, making sure you aren't hitting any latency. You want to not get in the way of that. And the other sort of half of this talk is about not getting bitten. So the GPU is going to be consuming a lot of resources, accessing a lot of objects whilst it's doing the work for you. You can on here use this texture, render this using this render pass, use these objects and whatever else. I've got this command buffer, for instance, all the lifetime management that others have talked about today. And if you touch any of that whilst it's actually being used, basically undefined behavior happens. You don't have any safety. Okay, that's not the clicker's fault. Good times. I just have to be vigilant, apparently. There it goes. So, yes, so you don't want to be deleting anything whilst it's being used, because then the GPU may see just data that's not there anymore. And if you update the contents of a texture, you may get the GPU reading it halfway through your update, for instance. So that can look like any number of things. If you're lucky, I say lucky, it's not really, nothing will be wrong, and you've screwed up, and it's all fine. For a little less lucky, you might get some tearing in your images, say like you've updated an image at the same time in 2 places and you're reading from another place and you get tearing. You may get image corruption. That's kind of bad. What? really not touching this. What is going on? Stop it.
Voice actually.
Or everything might just explode during your day, and then, oh no, everything's shut down. Never mind. Well, apparently it's got a lovely green border for sharing its monitor. Fine. What? Ah! Those of you on the phone are not really sure what's going on. The laptop's kind of doing things on its own. I don't know why. So it's really helpful. So, onto the serious bits, unless the most again. So it's a bit of terminology just to set you up for what I'm about to talk about. When I say an operation, I basically mean a set of something that can be executed on the GPU, some work that the GPU is going to have to get done. And very importantly, this actually includes synchronization events. So if you have something that's setting an event to signal it, or waiting on an event, that is a task and an operation in and of itself. Execution dependencies, these are basically a task saying, I depend on another task. So you might have some draw call that depends on an earlier draw call finishing, and that's a dependency. If you're expressing that dependency, that's an execution dependency. There's also memory barriers. Now this doesn't mean the same thing as GL. I'll explain more about that, what the difference is in a minute. But a memory barrier effectively is an operation that flushes and validates caches and basically determines what parts of the pipeline, what parts of the GPU can see the results of other things that have been written or accessed. And finally, a memory dependency is a combination of those two things. It's basically an execution dependency where one or a couple of the top operations that are being depended on are in fact memory barriers. So there's three rough buckets that you can sort synchronization types into in Vulkan. The first type is very fine-grained. These are pipeline barriers and Subpass dependencies. All of these operate within queues and typically within a command buffer. They can span multiple command buffers. And they all have very explicit memory dependencies and have very fine-grained control over the execution dependencies as well. There's also semaphores. Now these are between different queues. You can use them within a single queue, but there's not huge amounts of point because in certain circumstances. They're typically used for synchronizing if you've got multiple queues on the system. And finally, fences. These are quite heavy, but they are useful. And these basically allow you to go, here's some work I've done on the queue, and when is it complete? That's basically what it's for, is to say when a set of queue operations is completed. This is in contrast to something like where GL has two quite coarse primitives, which is the memory barrier, which again, very vaguely mentioning, but I will cover more detail why that's different, and fences. And they're both kind of similar to the same concepts here, but there are differences. So the first of these fine-grained ones is a pipeline barrier. And you can see on the right, I've put the command that generates a pipeline barrier. On the right, it's quite detailed, there's quite a lot of stuff in there. There's a set of pipeline stages. So rather than just saying, I want to, sorry, let me just take a step back. They basically say, I want to synchronize what went before with what's coming after this command at a sort of high level. But you actually specify a precise set of pipeline stages that are synchronized. So you might synchronize the vertex stage of a previous draw call with the fragment stage of the next draw call, for instance, something like that. And that you would express in these stage masks. So in the source stage mask, you say vertex stage, and in the destination, you put the fragment stage for that particular example. There's also a set of memory barriers expressing any memory accesses you're doing in those. I won't go into them just now, I'll come back around to that in a minute. But the key thing is that they are a single point in time. It's everything before with everything after within the constraints of the RPG provided. And a pipeline barrier, when you execute one, if you provide the appropriate memory barriers, that's basically equivalent to what a GL memory barrier is. GL memory barrier is a memory barrier plus an execution dependency. So it effectively expresses a full memory dependency in GL at a quite coarse level. Whereas a pipeline barrier does not necessarily have to express both. So an event is kind of similar to a pipeline barrier. There's a bit more to it though. So firstly, it's actually an object rather than just a command that you put in a command buffer. You have a VK event object. And the reason for this is that they operate over a range. You don't just say it's this before and that after. You start it at some point and then you wait on it later. So it's signaled and then waited This actually means they have a state, so they have an unsignaled state and a signaled state. It means you have a set operation to signal it and a reset operation to unsignal it. Each of these, again, takes a stage mask. So you can say in the set and reset, you can say at what stage does this trigger. So if you say vertex stage again, then after the previous draw calls before that command are finished, at the vertex stage, that's when that event will trigger. And then in the wait, you have pretty much the same info you have in the pipeline event, where you have to duplicate that stage mask so we know what you're talking about, because again, it may not even be the same command buffer. And you also have the destination stages as well, so that you know what you're waiting on. They also have this nice property where you can have some CPU interaction with them. It's a lot more simplistic when you're doing stuff on the CPU, because there's not really any pipeline stages on the CPU. You're just synchronizing with whatever you've decided you are doing on the CPU. So very simply, you can set them, you can reset them the same as you can in a command buffer. And you can also get the status. There's no explicit wait. You'll notice you can obviously do a spin lock, but the whole purpose and point of the event is meant to be very lightweight. So it's not really meant to be an OS primitive necessarily. So there's not particularly going to be a faster way that the implementation could do a wait for you. You're just going to have to figure it out. This does come with a bit of caveat at the moment. So if you submitted a command buffer waiting on an event, and you intended to set that, so signal it on the CPU, you have to be careful to set that pretty soon after you submitted the queue, submitted the queue, because there is a possibility that the OS may actually time you out, and thus you'll lose your device, and all that rendering you've just done has gone to waste. So unless you really need it, it's a good idea to ask yourself, can you just defer the submission? There are some use cases such as late latching of data, potentially for VR maybe, but they are very specialized and it's worth thinking about it before you do it. So they both specify similar things, so there's obviously a question of when do you use each. Pipeline barriers are basically intended for when you have the operation that you're depending on happening right before the operation that is going to depend on it. So there's no work in between. Probably cheaper and easier to use a pipeline barrier. You just create an object. It's likely that implementation may do a faster thing than just passing the whole object, event object into the chain. So that's when you use it. However, ideally you want to be moving to a situation where you can put some work in between dependent events, because that gives the GPU more opportunity to pipeline work like we showed in the first stage. And in that situation, that's when you want to use an event, because then you can set the event immediately after your first operation, and then wait on it immediately before the next operation. And then in between, any work that you do will be pipelined alongside it. It's not dependent. That's the idea. So before I get on to subpass dependencies, I'll circle back to memory barriers. So there's 3 different types of memory barrier in Vulkan, and it's a little bit of a balancing act which ones you use, although there are specific uses for all of them. So the first one is the global memory barrier. This one's red. No? Skipping again. First one is the global memory barrier. So this sort of sets you up for the rest of them as well. This is the most simple kind of barrier you can do. It basically just says what stage is accessing what memory and where is it flushing to, so that I'm going to be able to view the results of that in another stage. And you'll notice that there are stage masks here again, and maybe you're asking, wait, hang on, these are going with the events, why am I specifying the stages again? The reason for that, well, firstly, they do match up somewhat. Again, I mentioned before that you don't have to specify an execution dependency and a memory dependency at the same time. You can do them separately, which is why you have part of the reason for explanation. It's also possible that you may want to have an execution dependency and not have a memory dependency for a particular stage. So it's specified twice, and there is some difference in how those masks are specified as well. The main use case for the global memory barrier is it's got a lot of resources, and they're just doing very simple transitioning. Like you're taking your uniform buffers from a previous frame and transitioning them to be written on the host. You might want to just do a global memory barrier to say, look, just take all this memory and let me have it. Buffer barriers are a little more complicated, but again, they've got the access masks. Rather than operating on all memory that's currently in flight. More attention. So rather than operating all memory in flight, it operates on a specific buffer and a specific range within that buffer, so you can be very precise with this. Obviously, if you're going to specify every byte with a single buffer barrier, that's kind of the case where you're going back and using a global memory barrier. The other thing they do specify is if you're sharing data between two different queues or more queues, you can actually change the queue as a shift when you're doing a memory barrier as well. So you can say my compute queue is moving into the graphics queue. They may just be shared as well. I believe Chris will be talking a little bit about that later. And finally, this is, again, another layer of complexity added on. So we've got everything we had in the buffer, except obviously it's a range of an image now, so that's not like width and height and offsets, it's sort of a set of array elements or bitmap levels as well. As well, they also have image layouts, which I can't remember if we talked about. I know we talked about it in the break. The idea of an image layout is that it sort of allows a driver, if you, let me find what it is first. It's basically, it's an abstract concept. So one of the image layouts may be general. You may have one that's suited for shader reads, one that's suited for frame overwrites. And the idea here is that it's sort of, you define your usage for an image up front, but then the layout says, this is the usage I'm going to do now. And it gives you a driver an opportunity to go, right, well, I support this compression scheme for this type of access, or this compression scheme for this type of access. I'm going to transition it to, or anything else it may want to do as well. Oh, and yeah, quick performance thing. If you do have it, find you end up having to switch very frequently, it may be better to use general. It may not. It depends on your use case. Again, as with everything, test, profile, read equals performance programs. So subpass dependencies. The reason I said I've done this last is it is slightly different. I mean, firstly, if you can remember from Andrew's slide, they are actually defined as part of a render pass when you first create it. You don't put them inline into a command buffer. So they're actually just a struct. They define a lot of the same things as the other two do, but they do it at a different rate. And rather than having explicit memory barriers, they just basically have the same flags that a global memory barrier does. So you can define those things here. One thing I didn't mention before is this dependency flag. So we already talked about, or Andrew already talked about the idea of having pixel local access for some input attachments. You can also do things like if you have an image, not an input attachment or a buffer, where you know you're only accessing a particular value from a particular pixel location, you can basically say, I have this dependency, I know that I'm only going to care about this dependency on a per pixel basis, then you can put that flag in there, and it allows you to specify a sort of more fine-grained, possibly more optimal dependency, particularly on a tile level, you can avoid flush. So there's actually a couple of variations on this. So typically a subpass dependency is between two subpasses. But you've also got self-dependencies, firstly, and this allows you to put a pipeline barrier within it, within subpass. This might be something you use if you're doing programmable blending, for instance. I'm not going to go into too much detail about how you would do that, but the idea is basically that you would wait on the previous stage using the dependency by region. There is a couple of limitations on when you use pipeline barrier in a render pass. You can only do forward progress, and you can't. It has to be by region if it's in a fragment stage. And the reason for that is that anything else would cause the tiler to flush. I'm not going to cover exactly why that's hugely bad. It's very bad for reasons I'm not going to go into, but anyone wants to ask afterwards, feel free. And then there's the other flavor is external dependencies. So this is if you set an event outside before the render pass has begun, you can then wait on it after, during render pass. And that allows you to do things like build up a drawing direct struct. Actually, I've got some examples, so let's have a look at them. So this is an example of how you might use a pipeline barrier, or actually two pipeline barriers. So texture uploads, Michael I think talked about it a bit earlier in terms of how you would do it with transferring data, what resources you use. The idea is basically that you need to have your source, if you're doing a staging buffer, you need to have your source resource and your destination resource. Both of them need to transition states at certain points, and you need to define all that as an application there. So here we've got a buffer memory barrier where I'm setting the access from host, right? So let's assume I've already written my data into a buffer, into some memory, a VK memory object I've mapped. So I've written to that. I now want to say, right, I've written to it. I now want to get it ready to transfer to the image. So that's what that first bit's doing. And then we have a source access mask for the image barrier. So that isn't coming from anywhere. I've not used the image before, so it's just starting from the clean slate. And I'm moving that to be written to via transfer operation. And similarly, I've got no previous layout. It's completely undefined, but I'm changing it into a layout where I'm going to be doing transfers to it. So that's what that is. Then the stage is in the actual pipeline barrier. When we get to it, I'm saying I've got the host bit, which says I did something on CPU, so that was my CPU writes that I've already done something in that memory, and then I'm writing it out via a transfer operation in the next bit, and then finally do the transfer. And then the bottom is basically just reversing the transfer, so coming out of the transfer and then moving to shape readability, so you can actually use that in shape. And then an example of subpass dependencies. So this is actually going to, I'm just going to cover the external ones because they're probably the most interesting thing. So firstly, the source and test subpass you usually set to a number that is an index of the subpass from the render pass. For an external dependency, you use this special value bk subpass external, which I think is -1. That's my payoff there. And so the example here is using a compute shader to basically do something with the geometry and figure out exactly what you're going to be drawing, some sort of cutting algorithm potentially, and then updating your drawing direct structures that you're going to be doing for your draw calls. So the idea here is that you've got your source stage is going to be compute shader, and then your destination stage is going to be draw direct stage. So draw direct stage is interesting. It's not just like actual shader stages in the pipeline stages. It's also all the weird fixed function bits that happen in between, including the draw direct read. That counts as the pipeline stage. And then the access masks, again, setting them to the appropriate things. So I'm writing from shader, and then I'm going to read it as indirect command. So that's what that's there. After we've set that up, in the subpass, then you can do your dispatch. You can set the event again with the same source stage as the subpass, so they have to match. And then you can transition it after you've started the render pass. You can do a wait event by using this external dependency, again with the same source stage, and the access masks and the pipeline stages match exactly the external dependency ones as well. And then after that, then you can use that to draw and direct a draw. So I'm actually going quite well. Last time I ran out of time, I did this in 12 minutes. So this is so much. I'm running out of time. So semaphores. So again, I said these are used to synchronize queues. So a lot more coarse-grained than what I talked about previously. The queue submit operation actually takes a number of different submissions at once, and each of those submissions can have a set of semaphores associated with it, both for waiting and to be signaled. There's also some implicit memory guarantees when you do this. There's no memory barrier associated with the semaphore, but what it does say is that once a semaphore has signaled, any memory that has been accessed by the things that are in that execution dependency are visible to future accesses on the same device. That's a bit of a mouthful. But they're not guaranteed to be visible to the host. So a very quick example of what this might be used for. The main thing you might be using for it right now is for WSI, for the Windows system stuff, particularly around the acquire. So when you do an acquire image, this will make more sense in the context of our example talk later. When you acquire an image from a swap chain, you will get a semaphore that will trigger when it's done. And then when you submit your command buffer, you're going to be drawing to that image. So you sort of need to know when you've actually been given it. You've got ownership of it. So you can pass that in and wait for it in the graphics submission. Then you can wait, again, put another semaphore in to wait on that graphics task to complete. And then when it's complete, you then want to present it back to the presentation engine. And to do that, you wait on that in the queue present. So that's relatively straightforward, as some of the other stuff I've talked about. It's actually even simpler if you have, like on Android, the presentation and graphics queue in the same queue. in that case, you only need the acquire semaphore for the acquire next image, because there's some implicit guarantees between operators on the same queue. And finally, fences. So these are used to synchronize queues CPU. They're really, really coarse-grained, more so than the submit info to the semaphores. They actually are per command rather than per submit. They, again, have the same sort of implicit guarantees as semaphores, so once they're done, they have the same exact things, again, not guaranteed to be visible to the host. GL's fences are quite similar to this, although they also incorporate some semaphore functionality, because you can wait from the GPU. But they're very vaguely similar to this, otherwise. Yeah, quick time to rush through this. So pretty much the main reason you would use these is to deal with multi-buffering. So if you've got multiple frames in flight and you've got dynamic data, you typically want to have multiple copies of resources in flight to be able to update it without serializing the GPU and CPU. So by having a number, the number I picked here is actually the same number of images I've got on my swap chain. That's typically what I'm paying for, because you usually want those values to match. And very conveniently, the acquire function actually gives you the index of the image you're about to use, and you can use that index to index into your other resources as well, and it all just sort of works, which is quite nice. So what you might do is acquire an image, have a, use that index, then wait for the fence for that image, wait for that particular index fence, so you're waiting for that previous time that frame executed effectively. And then reset that fence so that you're ready to use it again. And you may change the data. Now that you know that fence is triggered, you can then change the data in the resources that are associated with that frame, which you know that frame is going to be executed. And then you can submit that stuff again with those resources and with that fence so that it gets triggered again. So again, you know when it's done. And last but not least, wait idle. This is really, really heavy weight. If anyone uses this in the rendering loop, you're doing that thing I said that was about to start serializing everything. So there's two flavors of this. There's queue wait idle, which waits for all queue operations, like queue submit, queue present to finish. It's sort of equivalent waiting on a fence for those queues. And then there's device wait idle. You'll notice that the prototypes are broken, just ignore that. And device wait idle will wait for all queues to, basically does VP queue wait idle for all queues, plus waits for some device operations that aren't part of the queue. These are kind of quite similar to GL finish, so they should use sparingly. The main reason these are here, and probably the only reason you should be using it, is for teardown. Basically, when you finish a wrap and you're done with everything, you want to destroy everything, and then use device wait idle and just go, right, I know everything's done, it's safe, I can delete it, I'm done. At every other time, please use other synchronization methods, because this is otherwise very bad. Really good over time, but not much. So this is hard. You've got to specify exactly the right amount of synchronization. If you do too much, you may end up serializing something you didn't intend to. If you miss anything, then you're going to hit data race conditions and bad stuff happens, potentially. The validation layers can help. I don't think they have too much in the way of synchronization help at the moment, though they are making progress. In particular, I'd suggest you pay attention to the pipeline stages, particularly for tilers. You want to make sure that you're not waiting on fragment stages if you don't have to. If you wait on the vertex stage, you get some nice overlap. But they do become intuitive as you use them. You just need to start thinking about it. Pay attention to image layouts. Think about how you're using them. Certain GPUs, not all of them, will make use of that. Again, it's something you really need to tune all platforms you care about, because a lot of them do not care. And so that's basically everything. So yes, keep the GPU fed without getting better. Do I have any time for questions? Probably not. Yeah?
It's the break, anyway.
Oh yes, break next, so it's fine. So you can either go and have a coffee or ask questions.
Any questions?
How do you handle resource transitions? As in, you described the synchronization as all of them are blocking. What I'm interested is on a GPU, when I'm doing using the DMA engine to copy resources to the GPU memory, why it's still using the graphics context? Is there any way to wait for a resource transition without blocking?
Well,
Sorry,
the,
I did not wait.
the transfer operations can actually be done asynchronously to the compute. I mean, the whole purpose of this explicit synchronization is that you don't wait on stuff that you don't have to. So basically, the idea would be, for that example, if it's on the same computer, for instance, what you would do is you would put in a set event just after you specify the command, and then you wait for it, And there's no guarantee in Vulkan that that will happen in order compared to the rest of the commands. All that you will be guaranteed is that when you get to that wait, after that wait has passed, you will have the result. So any GPU is capable of doing that asynchronously, and everything else will just be able to do so.
Typically, in this use scenario, there's a waiting for resource transition for multiple frames. So just streaming resources. I'm only using a subset of the frame for transfer.
Could you put the mic on your mouth? Yeah.
I'm sorry. The reason I'm doing this is streaming resources in a large amount of resources into GPU memory.
Right. So you went streaming from the CPU, or?
Yes, and pretty much what I'm doing is transition large number of buffers, and don't wait until they really just activate and start using them. The way it's handled it in normal OpenGL4 is do two separate contexts. Do the transition in second context, then do a GL finish to force.
So the thing of that is that it doesn't necessarily guarantee to be doing this in GPU. The main reason we have done it typically is so that you're not, right? It's so that you're not blocking your CPU and rather your GPU.
Yeah.
Right? You can still do that. I mean, you can build your command buffer for your transfer operations on another thread, for instance, and then when you submit again, it's meant to be very lightweight. So once that thing is ready, you pass it back to your submission thread and just submit it. And there's no CPU store going on there at all. It's just being done elsewhere. That's all.
Yeah.
Is there any other questions or on the call at all?
Okay.
The call is on mute, so yeah.
Yeah.